Hello there and welcome back to Bango Tutoring. In this video we're going to be looking at atoms and isotopes, and this is video 1 out of 3 for our module on atomic structure. Let's get right into it. So the first thing you need to know is that atoms are very small. They are the smallest atomic particles. Anything smaller than this is known as subatomic. So anything smaller than an atom, that's subatomic. An atom is about 1 times 10 to the negative 10 meters in diameter. So if you compare this coin to the moon, you can compare an atom to this coin. So the ratio of size between this coin and the moon is about the same as the ratio between this atom and this coin. So an atom is very small. So if you study chemistry, you might know this already because it's common content between the courses. What are the subatomic particles? Well, the subatomic particles are protons, neutrons and electrons. What are the charges on those subatomic particles? And remember from our module on electricity, charge is just a fundamental property of matter. Protons are positive, neutrons are neutral and electrons are negative. What are the relative masses of those subatomic particles? Protons have a relative mass of 1. Neutrons have a relative mass of 1 and electrons have a very small mass. So the mass of protons and the mass of neutrons are very similar. Electrons are much smaller compared to protons and neutrons in mass. Where are each of the subatomic particles found? Protons are found in the nucleus of an atom, the centre. Neutrons are also found in the centre, or the nucleus. Electrons orbit the nucleus in something known as a shell. So both protons and neutrons are found in the centre, or the nucleus, and electrons orbit around that nucleus of an atom. So this is a diagram which shows an atom. This is not to scale, by the way, but you have in the middle the nucleus, and the nucleus holds protons and neutrons, and that's shown here. So in the middle we've got our protons and neutrons all together. And around the outside we have our electrons. And as you can see, these electrons are positioned in what is known as a shell. And the shell on this diagram is just a circle. So there's 2 electrons in this first shell, and there's 1 electron in this second shell, rather. So as you can see, the electrons are not in the middle, they're not in the nucleus. Instead, they are on the outside of the atom. And what they actually do is they orbit. They're always moving, electrons, always moving around the nucleus of an atom. So the centre of the atom is where the nucleus is. This is the positively charged part, with protons dictating this. So we know that the centre of an atom is positive because, as we know already, neutrons are neutral, they don't have charge, but protons are positive. And because protons are positive, the overall charge of the nucleus is positive because you find protons there. Electrons being negative, well, that means because you don't have any protons or neutrons to balance that, the shells of the shells of the atom, or the parts on the outside, they have a net negative charge. So the circles around the atom show shells or energy levels. These shells house electrons which are negative. So on this diagram there's 2 shells, and they house or keep in the electrons which go around the nucleus. So the nucleus. The nucleus is less than 1/10,000th of the radius of an atom. So if we go back to our diagram, the radius of a nucleus is less than 1/10,000th of the radius of an atom. However, most of the atom's mass is concentrated here. So going back to our nucleus, the middle of the atom, our nucleus is the house, or where most of the mass of that atom is stored. So if you think of an atom, most of the mass is actually in this tiny little space, the nucleus. So electrons are arranged at different distances away from the nucleus. These are in different shells or energy levels. An uncharged atom will have the same amount of electrons as protons. It is neutral in charge. So if you have an atom which is of neutral charge, there is no overall charge in that atom, you will have the same amount of electrons as you do protons. So if you take, let's say, oxygen, and you have a certain amount of protons in the nucleus and a certain amount of electrons in the shells, if those numbers are equal, it means that atom is not charged. If that atom has lost some electrons, it will have an overall positive charge, and that's called an ion. So, later on in the course, you will study waves and electromagnetic radiation, but that's still a little bit far down the line. That's when we study waves. Electromagnetic radiation is a type of transverse wave which carries energy. Now, electrons are arranged around the nucleus, as we've already seen. The electron arrangements may change with the absorption of electromagnetic radiation. It will move further from the nucleus to a higher energy level. So, electromagnetic radiation, X-rays are an example of electromagnetic radiation, and so are gamma rays. If you take some of these high energy electromagnetic waves and you fire them at an atom, what you will find is sometimes that atom will absorb that electromagnetic radiation, and it will use that energy to move the electrons into a different energy level. So if you are firing X-rays or gamma rays at an atom and it absorbs that energy, you might find that the electron moves to a different shell. The emission of electromagnetic radiation means that the electron will move closer to the nucleus, or it will travel to a lower energy level. So if you have an electron moving towards the centre of that atom, it actually may emit electromagnetic radiation. So when the electron moves towards the nucleus, it emits electromagnetic radiation. But if it moves away from the nucleus, it might have absorbed some electromagnetic radiation. This makes sense. When the atom absorbs energy, as energy is always conserved, the energy has to go somewhere. It pushes the electron to a higher energy level that is further away from the nucleus. When radiation is emitted, it returns to a lower energy level. So, as you can see, we have this electromagnetic radiation going in towards this energy level here, and what you find is the electron moves from this energy level up to the higher energy level. So we'll replay that. Electromagnetic radiation hits the atom, the electron gains energy from that electromagnetic radiation, and it moves towards the outer shell, a higher energy level. This time, we're going to get this electron here, which gives off electromagnetic radiation and moves towards the centre. If you're following along in your revision workbook, pause the video now and complete task number 1. Okay, so we're going to move on to charges on an atom now. Atoms have no overall electric charge. This is because the amount of protons is equal to the amount of electrons. We've already been over this. The amount of protons in the nucleus is equal to the amount of electrons around the outside of the atom. And if it's equal, there's no overall charge. Elements are the basics of our existence. Everything which we can see, feel and touch is made up of elements, either pure elements or elements mixed together known as compounds. All atoms of a particular element have the same number of protons. So, again, if you pick something like helium, you know that all of the atoms within that material of helium will have the same amount of protons. They will have 2 protons, because it's the amount of protons which dictates what element that atom makes up. This is known as the atomic number. So helium has an atomic number, or a proton number, that's sometimes called a proton number, of 2. There are 2 protons in helium. The atomic number of helium is 2. If you have a periodic table and you have 2 numbers on that periodic table, they mean something. And usually the top number, that's the atomic number. This is the amount of protons in an atom of this element. So we used an example of helium that would have an atomic number of 2. Carbon has an atomic number of 6. There are 6 protons in the nucleus of elements of carbon. So atoms which make up the element carbon have 6 protons in their nucleus. The mass number, that's the total amount of protons and neutrons in the element. So the mass number of carbon, or this specific type of carbon, is 12. So that means there's 6 protons plus 6 neutrons. Now, sometimes if you look at complex periodic tables, you get a point and then some number here. But usually you just ignore that. You don't need to worry about that. If you study sort of A-level chemistry or physics, you'll cover that. But for now, just ignore the decimal places and just look at the 12, because that means there's 12 neutrons and protons in total. So, have a go yourself. How many protons are there in this atom of this element? Well, let's have a look at this element. There are 11 protons in this element because the smallest number here is 11, and that means there's 11 protons in this element. How many electrons are there in an atom of this element? Well, because there's 11 protons, it means there's 11 electrons, because remember, atoms don't have an overall charge. So if there's 11 protons, there must be 11 electrons. How many neutrons are in this atom of this element? Well, we know that the mass number is 23. So the mass number subtract the atomic number will equal the amount of neutrons. So 23 take away 11, well, that's 12. So there are 12 neutrons in this element, sodium. An isotope is just an atom of an element, but with different amounts of neutrons. This means it is still the same element. The proton number or atomic number hasn't changed, but it may be lighter or heavier. How might the amount of neutrons affect the mass number? Remember, the mass number is the amount of protons and neutrons, the total amount of protons and neutrons. So if you have a different amount of neutrons, you are going to have a different amount, or you're going to have a different mass number. So if the amount of neutrons change, the mass number will also change. Carbon has different isotopes. So there's carbon-12, carbon-13, and carbon-14. Carbon-12 makes up 98.9% of carbon found wherever. Carbon-13, that makes up 1.1% of all carbon, and carbon-14, that's less than 0.1%. It's less than 0.1%. So, if we have carbon-12, we have 6 protons and 6 neutrons. Carbon-13, well, that has 6 protons and 7 neutrons. Carbon-14, that has 6 protons and 8 neutrons. So carbon-12, that's the mass number. The mass number is 12 because we have 6 plus 6. Carbon-13, that's 6 plus 7. And carbon-14, that's 6 plus 8. Ions. An atom has the same amount of protons as electrons, which we've covered quite a lot. An ion is a charged atom. An atom with more or less electrons than standard. If an ion is negatively charged, it is an atom with more electrons, since electrons are negative. So if you have a negatively charged atom, it's an ion, and it's a negative ion. And the reason it is a negative ion is because it has more electrons, it has more negative charge. If it is positively charged, it is an atom with less electrons. The positive protons then outnumber the electrons, and the overall charge is positive. So if you have more protons than electrons, then the charge in that ion is going to be positive. Right, we're going to try and fill in the gaps of this little table here. Now, remember that the atomic number is the amount of protons. So, the atomic number here for element 1 is 17. So, how many protons does it have? 17. If the atomic number is 17, the amount of protons is 17. Remember that if the charge is 0, then the amount of electrons is equal to the amount of protons. So this table here tells us that our charge is 0. If there is a 0 overall charge, it means the amount of protons and the amount of electrons must be the same to keep the charge at 0. So if we have 17 protons, we must have 17 electrons. Okay? Now, the table tells us that we have 19 neutrons. Remember, electrons have very, very, very little mass. So our mass number is equal to the total amount of protons plus the total amount of neutrons. So 19 plus 17 is 36. So our mass number is 36. For row 2, you apply the same principles. Our mass number given to us is 180. That means the amount of protons plus the amount of neutrons equals 180. which means there must be 71 protons. Now, if there's 71 protons and they were charged at 0, we know that the atomic number is 71 because there's 71 protons. If you're following along in your revision workbook, pause the video now and complete task number 2. And moving on. So, one of the things that you need to know for your exam, which stems away from physics really and goes towards the scientific method, is that science changes over time. So, over time, new discoveries are made and new tests are carried out and new hypotheses are made and results are found from those experiments. Those experiments are then repeated by other scientists, and other scientists will review the outcome of those experiments, and if the reviews are overwhelmingly successful, then scientists may change their knowledge of whatever to suit the new discovery. It will become accepted. New experimental evidence may lead to a scientific model being changed or replaced. Before the discovery of the electron, atoms were thought to be tiny spheres that could not be divided. So until the discovery of the electron, atoms were thought to just be spheres that you couldn't divide anymore. That was the smallest thing that you could get, an atom. But then they discovered the electron, which came from an atom, so they thought, oh, there must be something inside this atom. The first model of the atom is the Dalton atom, or Dalton's atom. So this is model number 1, and this was written, or this was known about, in the early 1800s. John Dalton proposed this, and that's why it's called the Dalton atom. John Dalton said that all matter consists of tiny particles called atoms. He also said that elements were characterised by their atomic mass. So John Dalton, he said that all matter consists of tiny particles. So he thought that the smallest thing that you could get, if you divided something into little bits continuously, the smallest thing you could come to was an atom. And he said that elements were characterised by their atomic mass, so the mass number. Then model number 2 came along, and this was the Plum pudding model. So the birthday of this was the 1890s. So in the 1890s, J.J. Thomson, he proposed the idea of the plum pudding model. So J.J. Thomson proposed that the atom looked like a plum pudding. It is simply balls of negative charge in a soup of positive charge. This model came about after the discovery of negatively charged parts of the atom, which we now know to be electrons. So the plum pudding model, that came about after the discovery of electrons. And the plum pudding model and J.J. Thomson's idea of an atom was that we have a sort of soup of positive charge, and within that positive charge, lots of negative charge, little bits of negative charge, which we now know are electrons. So that's the plum pudding model, and the reason it's called the plum pudding model is because this looks a little bit like a plum pudding. You have like the cake bit of the plum pudding model. The cake part of the plum pudding is the positive bit, and within a plum pudding you've got little bits of plum, and that's obviously our negative charge, which is within the positive charge. Ernest Rutherford disagreed with Thomson's model of the atom. He thought that the atom had areas of positive charge and areas of negative charge. So J.J. Thomson thought that the atom was this super positive charge with negative bits scattered inside, but Ernest Rutherford disagreed with Thomson, and he thought that the atom had areas of positive charge and areas of negative charge rather than it all being jumbled together. He decided to conduct a rather famous experiment, the alpha scattering experiment, which included firing alpha particles at a thin sheet of gold. Okay, so the alpha particles, they have a positive charge. So the positive charge, well, you would think that they would be attracted to the negative parts of an atom and be repelled by positive parts of an atom. Next came along the atomic model, and Ernest Rutherford, the person who done the experiment, the alpha scattering experiment, he proposed this, and the birthday of this model was the 1910s, and this is obviously the model number 3. So from the alpha scattering experiment, he realised that the atom had a core, which was positively charged and dense. His work also showed that electrons orbited the centre, randomly. Ernest said that the electrons orbited the positive centre like planets and a sun. So, the alpha scattering experiment revealed that when you throw these particles, these alpha particles, which have a positive charge overall, when you throw these particles at a very, very, very thin sheet of gold, only one atom thick, he found that most of these atoms went straight through. Sorry, most of these alpha particles went straight through. So the alpha particles, which were positively charged, the vast, vast majority of them went straight through the gold and were detected on the other side. Few of these alpha particles went through and were deflected. So they went through the gold, but they changed the path. So let's say it was going to go like that. When it went through the gold, it went through the gold and then changed its path, it changed its route. And very, very, very few of these alpha particles, which were chucked at this gold sheet, came right back. So they didn't go through at all. They actually bounced right back. So he thought, because these were positive, there must be a very, 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 very small part of the atom which is positively charged and is repelling these alpha particles and sending them right back. And most of the atom must be air, because most of these alpha particles were just going straight through. And because some of them were deflected very slightly, that also led to him believing that there's a small part of the atom which is positively charged, which is repelling these alpha particles and sending them in a different direction. Model number 4, I know there's a lot to learn here, but it's part of the GCSE. Again, the birthday of this was in the 1910s, and it was Niels Bohr who suggested this atomic model. Niels Bohr didn't agree with the electrons being randomly arranged. His work led to the discovery of shells for the electrons. So Niels Bohr, he said, yes, there are electrons, but I believe they are arranged in shells. And that's shown in this diagram here. So the electrons are arranged in shells rather than just being randomly scattered like this. The further away from the nucleus you go, the higher the energy level. So that's confirmed nowadays, we know that. And it was Niels Bohr who suggested this. Finally, model number 5. This was, the birthday of this was 1930, so this model was thought of in the 1930s, and it was James Chadwick which came up with this model. Chadwick's work in the 1930s revealed that the nucleus is not just a positive sphere of positive charge, but it consists of both protons and a new phenomenon known as neutrons. So James Chadwick discovered the neutron. Neutrons are neutral in charge, but equal in mass to protons. So in the 1930s, James Chadwick came along and said, yes, the middle is positive, but there's also neutral particles in there as well. Neutrons. Complete task number 3 in your atomic structure workbook if you are following along. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.